Every digital system you use operates on a simple rule. A variable is either a 0 or a 1. But when you start combining thousands of these binary switches, the resulting logic circuits become immensely complex. If you're an engineer looking at a tangled web of logic gates, you need a way to mathematically prove exactly what that circuit is doing in a standardized format. To do that, we rely on the definitive map of any Boolean function, the truth table. A truth table lists every combination of inputs, labeled x, y, and z, showing if the final output is 0 or 1. While perfectly mapping the logic, it isn't an equation. To build a circuit, we translate this map into standardized mathematical algebra. Mathematics provides two canonical, or universally standardized, ways to write this equation. One path builds the formula using only the true outputs, while the other builds it using only the false outputs. Let's start with the first path here. We ignore the zeros entirely, focusing exclusively on rows where the assumption's output is exactly 1. This chart shows a truth table, looking only at the true outcomes. Each row generates a minterm, an atomic unit linking variables using the AND operator. By extracting them, we get discrete expressions, like x, y, z naught, or x, y naught, z. To combine these individual minterms into a single equation, we link them using the OR operator, which functions like mathematical addition. We are creating a sum of products. In Boolean algebra, this resulting standardized equation is called disjunctive normal form, or DNF. By literally adding together all the specific conditions that make the circuit's logic true, DNF gives us a reliable, universal standard. But we can also approach the logic from the exact opposite direction. We can define the function by analyzing when it fails, the zeros. Instead of minterms, this path relies on max terms. A max term is the structural opposite. Variables within it are linked together using the OR operator. This chart shows our method. We add a completely new column, labeled f', representing the exact opposite of the original function. Look at them side by side. Wherever the original function is 0, the f' column becomes 1. It is a perfect inversion. Now we treat f' like a standard function. We find true rows in that new column and generate its sum of minterms, its disjunctive normal form. But we don't want the equation for f'. We need the equation for our original function. To get it, we apply De Morgan's laws to flip the entire inverted equation back. De Morgan's laws dictate a strict inversion. Every AND flips to an OR, every OR flips to an AND every 1 flips to 0. By running the entire expression through this translation, our sum of products mathematically transforms into a product of sums. We call this conjunctive normal form, or CNF. It is our second canonical form, building the exact same logical architecture by mapping out all the function's false conditions. When we look at the DNF and CNF equations side by side, their structural differences are stark. Yet, despite looking like completely different mathematical languages, they express the exact same logical reality. Both disjunctive and conjunctive normal forms act as universally recognized standards across the field of computer science. Any Boolean expression, no matter how tangled or chaotic it might appear on paper, can be mathematically forced into one of these two predictable formats. Mastering these two paths, mapping a system through its truths or its falsities, gives engineers the precision required to verify and simplify the logic powering digital hardware.